Hi, in this session, I'll be discussing eigenvalues and eigenvector, one of the important concepts in linear algebra. We use the concept of eigenvalues and eigenvector in several models and algorithms such as factor analysis and principal component analysis for dimensionality reduction and in Markov chain for finding stationary distribution. Before we try to understand eigenvalues and eigenvector, let us try to understand product of two matrices. I am going to use a linear system of equations to explain the geometric interpretation of matrix multiplication. Consider the following two system of equation. 2x minus y is 10 and x plus y is 8. I can write this in the matrix form as first matrix, I am going to call that matrix A, 2 minus 1 and 1 1 times matrix B, which is a column vector x y, and on the right hand side we have column vector C with elements 10 and 8. Let us look at matrix A, more specifically column view of matrix A. I can write the matrix product as x times the column vector 2 1 plus y times the column vector minus 1 and 1. On the right hand side we have column vector 10 and 8. Here we are doing scalar transformation of vector 2 1 by x, and similarly we are transforming vector minus 1 and 1 by y, and the resulting vector is 10 comma 8. So basically matrix multiplication gives us linear transformation. Solving this system of equations, we get the value of x as 6 and y as 2. We can represent these transformations geometrically using graph here, in which we have first two vectors, its scalar transformation and addition of those two resulting in third vector. Basically matrix operations such as multiplication give us linear transformation, and we can use geometry to understand the impact of such transformation. Now let us look at eigenvalues and eigenvectors. Let A be a square matrix of size n by n and x be a column vector. The following relationship is known as eigenvalue problem, which is Ax is same as lambda x. Here the lambda is scalar called eigenvalue and x is the eigenvector. The equation Ax equal to lambda x can be written as A minus lambda I times x equal to 0, where I is the identity matrix. This has a trivial solution in which x equal to 0, that is not of our interest. Another solution is determinant of A minus lambda I equal to 0. Eigenvector is a vector whose direction remains unchanged when a linear transformation is applied to it. Here what we see is we are multiplying A with x, and the right hand side the x is retained, it is just simply multiplied with lambda. So the transformation results in simple scaling. Here is an example of geometric interpretation of eigenvalue and eigenvector from Wikipedia. Here we have a picture of Mona Lisa, and each point on the picture can be represented as a vector. After transformation, we can see that the vector blue has not changed the direction. This is eigenvector. Its length is also unchanged, thus the eigenvalue is 1. Geometrically, Ax equal to lambda x means that under transformation by A, eigenvectors experience only changes in the magnitude or sign, but the orientation of Ax is same as x. Eigenvalue is simply the magnitude of stretch or shrinkage on the eigenvector when subjected to linear transformation by A. The page ranking algorithm used by Google for ranking website for display when a keyword is entered by an user is an eigenvector problem. An article by Kurt Bryan and Tanya titled The $25 billion Eigenvector, the linear algebra behind Google, explained how eigenvector was used within Google for page ranking algorithm.